it's not an intense program today. We're really talking about the rest of the material on the first exam and a little bit of introduction, which starts after that. And so I sent you separately a couple of these chapters. I can't put them on Blackboard. They're too large. I particularly like the animations. The animations in this particular one are not great. So I'm really not that concerned about looking at those. Oops. They get a lot better, as you will see. Nevertheless, effectively, when it comes to a membrane, we know the basis is a phospholipid bilayer. You put phospholipids in water, they instinctively, wrong term, they chemically form a bilayer. You don't have to encourage them to do that. Because of that, the terms, okay, I was just going to stop looking at the messages. Because of that, okay, we don't have to concern ourselves about putting them together or anything like that. They are naturally going to form that way. And the magic of the bilayer, as you can see, the membrane is about 75% phospholipids. You don't have to really know about the numbers. Glycolipids have a separate role we're really not looking into. Cholesterol is a stabilizer. These are all by their very nature fats or lipids. Bless you. And either term will do for the time being. The beauty of the bilayer is, again, the membrane is relatively thin, and that's where the terms hydrophobic are so important. They're in the middle. Thin layer. The hydrophilic, the heads, point out and point in. Whether it's a membrane or an organelle, it doesn't matter, because the external environment and the internal environment, other than the membrane, are bathed in water. So here, we can basically, through the magic of, as you will see, the proteins that are there, be able to impact what's going on inside or outside of that cell, or inside or outside of that organelle, by working our way through the proteins that are embedded, and even sometimes, if necessary, actually working our way through the membrane itself. You'll see down the road that if we talk about steroidal hormones like testosterone or progesterone or estrogen, all the names we're surely familiar with, those we don't have to worry about. They're so small because they're made from cholesterol, they can get right through the membrane. They bond to what's called a receptor inside the cell. They get right through the nuclear membrane, so they go from outside the cell into an organelle, and they immediately affect something we talked about yesterday, transcription and translation. That's a very profound thing to say, that they immediately start working on. So when there's a boost of testosterone, estrogen, or progesterone at puberty, you can imagine it immediately starts a tumultuous amount of production of materials based on the genetic code. Gives you, it's a pretty good example. And you'll see some examples of the way it works in the other direction, when it doesn't go through the membrane. So here are the phospholipids, here's the bilayer. Yeah. Seen that all before. I spent all that time with the stupid folding and the paper and blah, 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 because the proteins are about their shape. And this gives you the 6 major roles. Ari, and I will, because the exam, I'm going to try this weekend, depending on how, if you hear a baby crying, understand Jackson is unhappy. I'm going to try to do my review recording and get that sent to you guys sometime over, so you have an ample time to listen to it a couple of times. And one of them is going to be basically what you're going to see. You're going to see these 6 different roles, and probably 5 or 6 of them will be, enzyme, receptor, cell-to-cell recognition, and that's the answer key. And then I'll have like 5 or 6 questions based on that answer key. So the challenge for you is to figure A, what the questions are, and B, what I'm asking about. That's the nature of this type of things. I'm going to try to give you somewhat of a heads up for this exam, because it's the first one. And whenever you have an exam with someone with whom you are unfamiliar with, that first exam is tough because you don't know the degree of detail. You don't know the style of the question, how difficult or easy, and the wording is so important. Someone contact me from one of the other classes, and that's fine, asking me if this was open book. I had an easy answer. No! None of these, all these, unless otherwise stated, are closed book. Let me tell you, this foolishness of saying, could we possibly have an open book? You don't want an open book. Because what happens is people fall into the trap of not studying. Oh, I'll just look it up when I get to the test. We're doing, teeny amount of studying. And it's timed. I mean, we have another class coming in. You're out the door, 50 minutes, bye. You're still on halfway through the questions because you've been busy looking up. You haven't looked at it before, haven't studied it, haven't organized. It's a two-edged sword. Careful. Don't say about be careful what you ask for. You might just get it. Recently stated. I know. I'm a real unpleasant person. I was going to use another word, but it's inappropriate. Okay. Membrane proteins. All of what they do. So basically, this is the way the external environment can impact the internal environment. They have a lot of mass. They have all these specialized functions. Integral and peripheral are not really, to me, important terms. Most of the proteins, the integral means they're within the membrane. Peripheral, they're on the outside and on the inside. Most of the proteins that we'll be talking about have outside and inside effects. Not necessarily all of them. I'm not going to ask you specifically about that. It's just a definitional thing, and you might run into it later. An integral protein means it's within the context of the membrane. Peripheral means it protrudes to the outside or to the inside of that particular membrane. From a definition, definitional questions by and large annoy me. So integral, firmly inserted, transmembrane, spanning the region. So again, because of the folding thing that I did, understand they can do that because there's enough of those R groups that are compatible with fat. They're what we call hydrophobic. They're afraid of water or resist water, that they're able to do that. Okay? And then we'll go into the functions in a second. Peripheral, loosely attached, who cares? But all the stuff on either the outside or the inside surface, support, we'll go into that in a second. This is horrible because you can't see it, but thankfully they blow it up. Here we are. Transport proteins. We'll get into what's called simple diffusion. For our purposes, that really does not necessarily involve these proteins that are embedded. It's really moving directly through the membrane. And we'll look at breathing with oxygen and carbon. Water would be a pore like this. Water's got its own kind of movement. It's something we'll get to, not today. A term that you've heard, and unfortunately I like ample time to explain it because students are always confused by osmosis. Okay? And that's something we're going to deal a little bit with today. Starting to understand the definitions or the terminology, which is part of it. So when we're doing movement, these are basic kind of solutes, that's the term, are hydrophilic, they like water. So we're going to be talking about things like sodium, potassium, chloride, various kinds of sugars, etc. All of those kinds of chemicals that are water soluble, relatively small. Collectively, their common name is solute. What a solute is, or solutes in the plural, is it's stuff dissolved in water. I like to use very sophisticated terminology. Anything that dissolves in water is a solute. Okay? The solvent, stuff with which it is dissolved in, for our purposes, water, living systems, it is the universal solvent. So we look a lot down the road at relationships of solutes to solvents. And the test question, and this is it's probably not pertinent so much to this exam, but the next I'll talk about movement of solute and movement of solvent. And then it's not a fair game to come up here. What are you talking about with solvent? That's one of those. My answer will be, I can't give you any more information. Okay? So I'm trying to warn you in advance. And again, that's a luxury you do have for my exams here that disappears. Oh, trust me, when you get into nursing and these others, they won't let you do that. So transport, and we're going to look at ones whether they pour, like for water, that are always open, or ones that for other solutes like sodium and potassium, which are frequently always open, or ones that are controlled openings, we call gates. Okay, and sometimes chemicals open the gate or close the gate. Electrical current plays that role. There's a lot of things that are there. And the other one that we will not get to, okay, which will come actually in the next section, is when we talk about active transport. That implies the use of energy. A lot of times we have to impart energy to overcome environmental conditions. And whenever we say that, we'll use the term active transport. And very often you see the term pump. The one you will hear the most about, not today, fortunately, is called a sodium potassium pump. It's the best understood of all the pumps. Pump means active transport. We can use the term interchangeably. So if you see it on a test, the word pump, you know that it's active transport. Even when we open and close membranes, we have to utilize energy. You'll see that biologically, like any living system, you try to be very conservative. You don't want to spend energy recklessly. Our bodies are very frugal when it comes to energy, so we try to find ways to do it with requiring less energy, or use our energy in such a way to get multiple uses out of it. And again, these are not particularly good animations. But in general, when we get to some of the ones that are more sophisticated, they're quite good. So the first one, as you can see that we covered, was transportation. Next one, signaling. Fancy name is signal transduction. Transduction basically means you're changing the message. And I mean, the classic example of this, down the road you'll see it's a classic example of something called facilitated diffusion, is insulin. Insulin is a giant water-soluble protein. It would destroy a membrane if it tried to get it. Physically, it cannot. Yet it has a remarkable impact. And indeed, just as it describes here, not all of them, but insulin does initiate a chain of chemical reactions inside the cell. And you'll learn a little bit about that in AP2 when you talk about the endocrine system, how it works through that. But effectively, this is an integral membrane with proteins on the inside and proteins on the outside, peripheral proteins. So when the insulin latches on here, basically it induces a shape change here. It's just if somebody walks into the room and we kind of glance over. Something happens from the outside that causes us to have an event inside. Someone knocks on the door when you're home, you go to answer the door. Maybe they ring the doorbell. Maybe you have a package you have to sign. Somebody you want to see and you make like you're not there. I like that one best. We hear people when those unsolicited. Your windows look like they could leave me alone. What do you sell? His dog bark very loud. He's very large, very scary. Wicked, but it's effective. Beware of the very overly loud, friendly dog. Nevertheless, the insulin strikes here, and what happens effectively by grabbing here, it creates a reaction on the inside, like me kicking at something. That causes a turn of events. Actually, it churns a series of proteins in here that cause the variety of effects insulin has, one of which is to open one of those aforementioned channels so that glucose can come in. It's not a one-to-one thing. We'll see. That's really what signal transduction is about. That's very common. Most of the communication cell to cell is based on chemical. Most of that communication is based on chemical. The example of this, you studied it a little bit when you were looking, maybe not directly so, because some of the other classes I had. Indigestive. Okay, you looked at epithelia. The hallmark epithelia of digestion is called simple columnar. Okay. Simple columnar, they are the busiest darn cells you can imagine because they're constantly busy, basically digesting and absorbing things and playing a variety of roles. They are so busy and under such pressure with chemicals, changes in pH, abrasive foods, that we replace all of them, the entire stomach, small and large intestine lining, every 3 to 6 days. Billions of cells daily are being replaced continuously. One of the things that they do is they have enzymes. They have something called microvilli. So each of these cells have fingers, and each of those fingers have cells along them, and each of those cells have additional fingers. All of them, as you get to this ultra microscopic, have what we call brush border enzymes. So we talked about sugars. That whole idea of lactose intolerant. One of the enzymes here is called lactase, and it will break the assuming you have it, not lactose intolerant, will break up the lactose into glucose and galactose, because in order to absorb it, it has to be in its monosaccharide form, either glucose or galactose. So that immediately is how these things are called brush border enzymes. You're going to see anatomically in AP2, all of these modifications are all about large amounts of surface area. Okay. The human body is replete, it's filled with lots of, you want to build, redundancy is a good term. Replacement parts is a good term. We have between, starting with your small intestine and large intestine, you got, 20, 22 feet of bowel. I mean, if something's gone wrong with one of them, if there's a giant ulcer, or if heaven forbid there's a tumor, or something bad happening, some terrible infection, okay, we can remove that. Okay, you can remove 6 inches. You can remove a foot. Maybe you can remove it in multiple places, sew it back together, and it'll work. That's the beauty of the system. You have so much of it, and you're not going to limit your ability to digest or absorb. So there's a whole lot that goes on with regard to these things. And I try to give you some context for what happens that are there. I mean, you're looking at somebody who's already had, half of my stomach removed twice. I know it hasn't affected itself in losing a meal. I get that. But it's all right. I didn't have what was called bariatric surgery. I didn't staple my stomach. I had very bad ulcers, which I'll tell you about down the road. And unfortunately, I have 2 major surgeries on that. The last of which was thankfully 25 years ago. Now we get into some really significant features. Recognition. The basis of recognition are glycoproteins. All cells protruding from their membrane have short chains of relatively small sugars like glucose and fructose. So they play other roles than just with being something that's an energy source. They are for identification. The combination of all of those sugars protruding creates a kind of sugar shell. The fancy name is glycocalyx. There are some cells where it's more dramatic than others. You'll see, and we're not the only things. Bacteria all have a sugar shell. So it's a feature of living membranes. Okay, the shell of sugars that are there. This one has to do with recognition. If you did not know, when you are born, your immune system really is just starting to function. It is not capable of protecting you. So you rely on what is passed on to you by way of at birth from your mother. Okay, so wherever you understand, I use the term birth mother because I have 3 adopted children. Okay, and so there's no statement. That's just a habit I've gotten into. All my kids knew they were adopted, as soon as we got them. And we got them at birth, so we started telling them right away. Nobody likes surprises. So, nevertheless, okay, so what happens, your mom provides you with a lot of cellular immunity and a lot of chemical immunity. What those cells start to do is you begin to produce them. They start going through your body. Okay, they're not ready to defend you. Mom's taking care of that. What they're doing is something called identifying self versus non-self. And all they do is they roll. There's no vision. It's a cell. It doesn't have any special talent. There's just masses of them. And they roll over structures, and all of those cells have sugars that protrude from them. They become familiar. They recognize them. That's the cell phase. After about 6 months, as your immune system ramps up, and there's a variable timing to it, at that point, now we have established what's you. Anything after that is unrecognized, is non-self. Now, in that first 6 months, if you got a virus, okay, your immune system wouldn't recognize the virus because your mom's immune system would attack it and control it. That's their responsibility. But once that sort of grace period is over, at that point, now if it comes across one of these and it was supposed to have a marker like that for normal, and all of a sudden the sugar's kind of an odd one was there, and it was like this, molecularly speaking, it latches onto it and starts a chain reaction that we call an immunological reaction, summoning more white cells to the area, releasing scads of chemicals. We have an invader, okay? And it's going to, it's just like you're in a military base and an invader came in. You have sentries there, you have guard dogs, you have the whole thing. You have all sorts of, arms pointing at them. That's the analogy I use when I teach immunology. So understand that is vital. The crux of those, an alteration of one or two of those little carbohydrates, is the distinction between my A positive blood and maybe your B neg, or your O positive, or your AB neg. Something as subtle as a couple of sugars alteration. That is how specific and how sensitive recognition is. To give you an idea. Attachment. You spent time, there's a word that you're having some kind of lab exam, the room. And one of the things you learned about were connective tissues, where epithelial cells aren't just linear. We belong now. Here, there's a square, simple cuboidal, simple columnar. They're sheets. They're all tethered together in a big sheet. Like in your blood vessel, okay, here's a blood vessel. That whole interior is a sheet. It's super smooth. It's made of simple fibers, right? So you can do this. Blood will go in there. It doesn't adhere, rolls, because when things roll into bumps, that forms blood clots. It's very straightforward. Connective tissue is connected. The cells are not all connected to one another. The cells are apart, and the fibers that it secretes connects them. They pull and tug on them. Pulling and tugging sends messages. Oh, we need more fibers because this cell is under a lot of trauma. Oh, stop making fibers. We've got plenty. Oxygen and carbon dioxide nutrients can't get through efficiently. So what connects tissue, and so that's why pulling on the outside, again, will have impact on the inside. So it's not in a vacuum. We'll look at inside the cell, it's called a cytoskeleton. There's a very sophisticated framework in the cell, and it's impacted by pulls and tugs from the outside. Proteins permit those fibers to attach. Just for instance. What you're hopefully getting is there's a lot of nuances with regard to what they can do. And then lastly, and we'll look at it separately, at the three different signature ways that it joins. They have a fancy name for these kinds of proteins. They call them CAMs. CAM stands for cell adhesion molecules. Believe me, that's one of the ones, if you came up and asked me, I would be more than happy to tell you the definition. Okay? Because I won't. But my questions, I'll talk about the different names for them and you'll see them shortly. They'll be pretty straightforward. More on that down the road as we begin to talk test stuff. And so again, this whole glycocalyx means sugar shell. Glyco for sugar. Calyx means shell, a hard shell. When you learn about it in micro, there's one called the calyce virus. It's a virus that has a very distinctive shell. So again, sticking out of the surface, and it's not just for identification. Proteins can be attached to it. Lipids can be attached to it. It's a framework for other things that could attach to it, as well as having that identity function that we talked about, or a joining function that we're going to talk about. There's a lot of different roles for this. And again, it's very interesting. Moreover, you and I, the only ones who have the same identity, if we talk about that from an identity standpoint, is either you with your own tissue, or if you happen to have an identical twin, which isn't terribly common, comparatively speaking. That's the basis of when we do transplantation. Okay? Somebody needs a kidney transplant, and they put a community-wide watch and say anybody who might be considering being a donor, what they do is they test for maybe 100 of these different markers, similar to you, as well as blood type. And maybe if you get, give me an arbitrary number, 80 out of 100, that means you potentially are a suitable match, and they'll do more testing. And obviously, someone would have to want to do that. And speaking of redundancy, why can you do that? If we got 2 kidneys, only need one, and you only need about a quarter of that one. Okay, quarter of 25% of one kidney to do exactly what it is. We have an immense amount of redundancy. So, I mean, I think of it as spare parts that are sort of incorporated. Do you want to do without them? Probably not. But if you had to, or if you had to donate, different. I was fortunate that whenever I did procedures like skin grafts, I didn't have to get skin from somebody else. I used their skin. So, and if it's your own, or I did a bone graft, I use their own bone. And that's something you don't have to worry about it not taking. It's theirs. It's going to take. So that's that whole self versus non-self that's there. And they give you a very interesting thing on it. Those little sugars change rapidly in cancer cells. And what it underscores, a general principle of medicine. Wanted to identify early and treat early. If you do not do this, things get out of hand. Okay? What cancers do, as you can see there, the cancer cells change so rapidly that the immune system, which is making something called a killer T cell or cytotoxic T cell, it's designed to latch onto one of those glycocalyx markers. And in doing so, once it attaches, it can destroy the cancer cell. The cancer cell is changing so fast, the markers are changing. As it's cloning itself and going all over the body, it's changing. So if we don't attack it early and powerfully, big problems. And that same principle goes over to treating infection. I spent my 25 years of my career treating patients, basically treating diabetics. Maybe up to 3/4 of my patients were diabetics. They get infections all the time. Their immune system is already compromised. And I used to tell them, I don't care when you call me. Okay, my answering service will get me. We had the old phone machines. I had one at home. I mean, it was long before these things existed. I said, I don't care if it's the middle of the night. I don't care if it's a holiday weekend. If you got a problem, you call me. We will meet in the office. We will meet in the emergency room. Because I know how rapidly an infection like that could end up in them getting gangrene and losing part of a limb. Doesn't take much. Early identification and treatment. So this is the last part. This is the last part that's on the first exam. These are the juncture points. There are 3. They are made out of proteins and have fibers that help to reinforce them. The 3 are called tight junctions, desmosomes, and gap junctions. If you think tight junction, it's easy. Think watertight. Desmosomes are the strongest, and as you will see, another name that is interchangeable with a gap junction is called a connexon or connexons. That's a junction that allows signals of either electrical, charged particles, or chemical to go from cell to cell. Your cells are always talking to each other. I showed you that pulling and tugging. That's a signal. Okay? There's nothing unusual about that whatsoever. We'll do a bone unit in here. You're going to see bone cells are going to communicate, indicating be more aggressive and make more bone, or bones being laid down on the other side, we don't have to use as much. We can leave them with some of our bone, remodel and go. This is a common thing that occurs biologically. So the signals are always there. So these are all, and with the exception of, on sperm cell, I really wouldn't, is a good example because I really don't think it's a true cell in a classic sense. Red cells and white cells are they function as an aggregate. They work as like an army of cells. Other than that, all the cells are somehow connected to other cells, either closely like epithelial cells, farther away by connective tissue cells, or cells that are in some type of a tissue for a particular purpose. So these are the junctions. These are proteins, integral proteins, part of the membrane, which allow cells to form together. It's like, and as you can see, prevents fluid and most molecules from moving in between cells. So take my example. What creates stomach ulcers is an abundance of acid. Your stomach's filled with acid. If you do dumb things like drink, which I didn't do, smoke excessively, which I did do, take non-steroidal anti-inflammatories like candy, which I did do, and have a very unhealthy lifestyle, which I did have, and had a lot of stress, which I did have. All of a sudden, I ended up with ulcers like this, described by my gastroenterologist who made the diagnosis as a train wreck. So, what happens is your cells, your lining cells in the stomach, are watertight. They have so many of these tight junctions, the acid can't get through. If the acid can't get through, it'll start to damage the area underneath the lining. And effectively, what an ulcer is, it's like someone took a sharp object and took a sharp scoop and carved out some of the underlying tissue. Somebody took a sharp, little ice cream scooper and took a chunk out, and they can bleed, and they can perforate, and you can die from it. No two ways back. I'll hopefully not entertain you with too many stories like that. We have them. Even further down in your gut, you have places where it's designed to let certain molecules go through. And the kidney is designed to let certain molecules go through. So sometimes we want space, sometimes we don't. So this is this upper one. Imagine these proteins that it's like a belt. And the more of those belts you have, if you stack them here, 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 and here, it makes the space, because one cell is attached to the other, it makes for very little space for anything to go through. Where it is most common to see this watertight appearance is in a very, very famous area called the blood-brain barrier. The capillaries in your brain do not allow water-soluble things to get through. So even medicines that work on your brain, whether they're medicines for metabolic diseases or medicines for psychological/psychiatric diseases, okay, they have to be fat soluble. We even engineer them pharmacologically to have the ability to pass through that membrane. To give you an idea, that's the most famous of the barriers, called the blood-brain barrier. If you want strength, imagine a cell that's moving constantly, more rapidly than once a second your entire lifetime. Those are your cardiac muscle cells. They are held together by a different juncture, this one. That's the desmosome. It's the strongest. It's stretchy like a zipper with interlocking teeth. Okay, so the teeth are there to hold it strong. And if you unzip it a little bit, it gives it a little bit more motion. Your one heart cell tells the next two contract, tells the next two after that contract. It's pulling and tugging. For a quarter of a second, they all uniformly pull in sequence, and then for the 3/4 of a second, they rest. More rapidly than once a second does your heart beat every second of your lifetime. If it doesn't, you will not be listening to this presentation. They have plaques. They talk about rivets, reinforcing like you would steel girders if you were building a giant skyscraper. It has keratin filaments. You learned about keratin for skin, a tremendously strong structural protein. Okay, and so that's what I mean when they're asking where it would be useful. You have this ability for these muscles, and moreover, they need to send signals to one another. So here's what it looks like. Here are these, basically linking together, giving it this quote zipper. Like, I don't know if it's a great analogy. Here are the plaques reinforcing it. Here are these filaments. You're going to learn about intermediate filaments. There is a lot of infrastructure inside your cell that are created by those. And in addition to having those at this juncture between heart muscle cells, it's got a fancy name you're going to learn about called intercalated disc. And that intercalated disc has a lot of surface area, again, reiterating the point of surface area. And it has desmosomes so the cells can pull and tug with a certain amount of give, but stay together for your life, hopefully. And on the other hand, they send electrical signals to one another for that sequence of things. I just contracted, now it's your turn, it's your turn, it's your turn. All of your cardiac muscles inside of a quarter of a second, starting at what's called the pacemaker all the way through. And that's because it has gap junctions or connexons, little tunnels that allow, in this case, ions, principally calcium and potassium, to send the message quickly. And so here are those they are proteins, they're very specific. The fact that opening is not for, we can have calcium or potassium or chloride go through it. No, they're all specific for one, maybe two items. that can get through. And effectively, that last slide is the very end of what is on your first exam. So anything else today starts the second exam, and it's just a brief introduction. The next big section we talk about is extraordinarily important. It's what we did all this stuff with proteins about. I even talked about it a little bit already. It's called movement across membranes. And biologically, some things can get through easily. If they're small, if they're fat soluble, okay, if they're non-polar covalent, like oxygen and carbon dioxide, if they're small, like cholesterol, which is a relatively small molecule, they can get through very, very easily. We call that process simple. Everything is based on what's called concentration. Large amounts of one molecule. At any temperature, they collide with one another. The closer they are together, the more collision, they go farther apart. They go from their concentration to lower. Anybody coming into the room here is not going to be able to sit in the front row. No more seats. Seat here, they're going to go where there's less people. Higher concentration to lower concentration. Unlike me, smaller particles can move faster. Bigger particles do not. I think it's like that. I can take it. It's okay. That's the way those things work. So, and certain things can move better through certain substances. So in your lung, have the lung part, the air in your lungs, is separated. There's a ton of oxygen. Okay? Very little carbon dioxide. There's some in the air that you breathe. And on one side, this goes back to mining cells, you have simple squamous. Attached to something from the base around. Very, very thin layer of protein materials. That and materials that allow stuff to pass through. On the other side, you have a capillary. The fancy name is pulmonary capillary. It has a ton of carbon dioxide, very little oxygen. Your blood doesn't lose all of the oxygen. If anything, gives it about a quarter of it. We call it deoxygen. On that side, you have simple squamous. The beauty of simple squamous is it's a giant amount of membrane. The middle of it has a nucleus, so it's got a ton of membrane that the stuff can pass through. So what happens immediately? There's an abundance of oxygen. Oxygen goes this way, carbon dioxide goes this way. And there could be more things. You have simple diffusion. Small, fat-compatible molecules like fats, or in this case, non-polar covalent like oxygen and carbon dioxide, move their concentration gradient at the same time. It's flipping a switch. It's not like, well, I'm oxygen, I go first. No. You all go at the same time. They move at different rates, having to do with something called solubility. We talk about that in AP2 when you look at pulmonary. But what it means, that's passive transport. It didn't require any energy. The body, again, is very frugal with regard to energy. So this is something we don't have to worry about. It's inherently part of the system. And we do the same thing again when we get to the cellular level, and then now oxygenated blood is providing oxygen at the cellular level and picking up the carbon dioxide. All of that's what your heart basically does. It's got two circulations, one to your body to deliver oxygen, one to your lungs to take the now relatively depleted deoxygenated blood and restore the appropriate amount of oxygen to it. And we just do that constantly. You learn about that when we talk about the anatomy and physiology in AP2 of the heart. So the idea of that's a classic example of passive transport. And that's simple diffusion. By definition, if we have one of those little passageways made out of protein and we can open or close it like insulin does sort of indirectly, that is facilitated diffusion. The insulin isn't like opening that big door and saying glucose come in. It's doing a number of reactions, one of which is to open passageways for glucose to come in. So effectively it's facilitating or enabling the diffusion because there's always more glucose outside than inside since the glucose coming in is immediately used. The reason I put the thing up there with solutes and solvents, okay, is this osmosis. That's the hard one, because we have to understand that if water has if stuff's in the water, there's still a concentration of water, and that I can't tell you how important that is, because it controls fluid entry and exit into our cells. And one of the really difficult things we have to deal with in life is if there's fluid going in or if there's fluid going out in excess. It can be immediately fatal. Okay, you cause your cells to shrink or cause your cells to burst. I mean, that's why we're so concerned about fluid and electrolyte imbalances. When elderly people or babies who really have very little reserve start vomiting and diarrhea, I mean, all of a sudden, systems start to shut down, particularly because of the electrolyte, the charged particles, hearts and brains and stuff like that. Nervous system doesn't send signals very, very efficiently. That's why this is so important. So here's the note about concentration, high-speed movement, random due to their intrinsic kinetic energy. They're always moving. They're not at absolute zero. You're at body temperature. Collisions, they move to a lower area. Everybody's done the stupid beaker with the ink or the dissolving dye, boom, like that. I told all the classes. It's amazing how rapidly that happens and how much pigment. A thimbleful of blood to turn a gallon of water. Gallon is a 4-liter beaker. Red. A little bit goes a long way. So even the dyes are not all created equal. So when we see large amounts of blood, somebody cuts themselves and the sink's filled with, you don't know whether it's, a couple of cc's or milliliters, or everybody say, oh my God, there's a gallon. You don't have much blood in you to talk about. So concentration, size, temperature, more collisions, the more movement. And we're seeking to reach something called equilibrium, where the net movement in your lungs, it's like that. There's always oxygen and carbon dioxide moving, but effectively the goal is to get the appropriate amount of carbon dioxide out of the blood that's coming, and so we can expel it in our lungs and bring the oxygen in. But even then, molecules are moving back and forth. We talk about the net movement. So we want to reach it when the net movement is molecules in one direction only. There is no net movement. So we either have stuff coming in or going out. It's equal. So, and that happens within a fraction of a second. I mean, your blood kind of takes about 3 seconds to get through your lungs. In the first quarter of a second, it's all oxygen. You'll see that that's really important because, again, that's another one of those neat safeguards. So we'll stop there. I'll leave you with that. Have a great weekend. Make sure if you didn't sign, make sure I get the sign-in sheet. Make sure you signed it. I want to make sure it gets processed. I'm going to do that before I leave today. Thank you. Hopefully it will be